Hi there, I'm Mr. Graves and I'm going to talk to you today about electricity. Now, electricity dominates our lives in the modern world. In the past, we used other things such as coal and oil and gas to heat our houses and to move our vehicles around, but more and more we're moving towards electricity. Houses are still generally heated using gas, but with global warming concerns and low carbon economies, we need to be moving more and more towards electricity. Cars are moving more and more towards electricity, but how many of us really understand what electricity is and how it works? Some people get through their exams just trying to memorize some stuff. We try and explain electricity by saying, think about water in a pipe, or think about a lorry dropping some stuff off at a shop and going back to the depot to buy some more things, or they say imagine some balls rolling down a hill. But none of that is actually saying what electricity is, and I think it's very straightforward to understand exactly what is going on if it can be explained properly. And if you understand something simply, you don't have to revise quite so much, because you actually understand what is going on. And that's what I'm going to try and do today. I'm going to try and explain to you exactly what electricity is, and what words like voltage, potential difference, charge, current, power and resistance. We all use these words at GCSE, but do we really understand what they mean and why we use those words? Okay, so let's go to the beginning. Things are made of atoms. I think we're quite confident that we all know that. And atoms themselves have got three parts to them. They have got protons, neutrons and electrons. Now today I'm not going to look at the neutrons because they don't have what we call an electric charge. I'm going to look at protons and I'm going to look at electrons. Now here is a very, very simple atom. It's a very simple atom, has got three protons in the center. It says neutrons there as well, but I'm not bothered about those because they don't have a charge when we're talking about electricity. So this atom here has got three positive charges in the nucleus, and to balance out those three positive charges in the nucleus, it has got three negative charges which are orbiting around the outside, and that makes up the whole of the atom. So the positive charges are called protons, and they're fixed. They cannot get out of that nucleus. The negative charges are called electrons, and they flow around, they orbit around the outside, and they can come and go and move around a little bit. Sorry, my dog is barking at the moment, so I'm just going to pause and I'll be right back. Okay, back again. Sorry about that. There was a pause while I dealt with the dog's paws. Right, so we were saying you have got positive charges stuck in the middle, negative charges going around the outside, and there are as many positives as there are negatives, and so this atom here has got no overall charge. It is a neutral atom, and that is the state that things like to be in. If they've got an opportunity, they will have as many pluses as minuses, so there's no electrical charge. There, we've used the word charge. And if something has got a charge, that means it's either got more positives than negatives or more negatives than positives. Right, so we got that. Now I'm going to do something called static electricity. We know all about that, and everyone gets very excited because it makes your hair stand up. I can't do that. But what I am going to do instead, I'm going to show a little demonstration of static electricity. I've got a nylon rod here, which I've borrowed from school, and we're using nylon because it is an electrical insulator. It is virtually impossible to get electricity moving through here, because for electricity to move, you have to move electrons, and they're all fixed and they don't move. So I've got this. I've also got a sort of fleecy jumper here, which is a man-made material, and that doesn't conduct electricity either. So what I'm going to do is I'm going to rub this here, and what I'm doing by doing this is the atoms on the outside of this rod, I've just rubbed some of the electrons off, and so they now have a positive charge because we've lost some of the negative electrons, and so this has got an electrical potential. We use potential. Anyway, it's lost electrons, it wants to get some electrons back. So I have here some little pieces of paper which I've torn up. Just going to give this another little wipe here, and it wants some electrons. So if I go close to that, you can see that it picks up those things there to replace the electrons that I've just rubbed off, and that goes flying up like that. Now if I want to take this charge away, I just wipe it with my hand, and the charge has gone because it's taken electrons back off of my hand while it was doing that. So you've seen this with rubbing a balloon on your jumper, you can stick it to the wall, that kind of stuff. And all you're doing is you're taking electrons off the outside of something. So you're wiping these electrons off here, so then it's left with a positive charge, and then it looks to get those electrons back. And the more electrons you take away, the higher the electrical potential it has. It has the potential to grab those electrons and bring them back again. So we have used the words charge, we've used the words potential. We're going to talk about potential difference in a little while. And if something's got a high potential, we say it's got a high voltage, because there's a big imbalance between the pluses and the minuses here. Now this is quite a simple thing to do on a small scale. Now we can do this on a much bigger scale if we have a Van der Graaf generator. Now this thing here, it runs off electricity, but that is not the static electricity. All that the electrical motor does is it spins around a belt that's inside here, and that belt goes round and round and round, and it's a rubber belt, and it's basically doing what I was doing with this rod and the jumper, is it's rubbing electrons off, and the electrons are rubbed off at the top here onto this area here, and then there's a metal ball that goes on the top, and all those spare electrons that have been rubbed onto there rather than onto the jumper gather around the outside of here. This is a piece of plastic, so all the electrons on here cannot get off, and they get more and more and more dumped on there, and you have a higher and a higher charge. And because there's a more imbalance, there's many more electrons than there are protons, we say it has a very high electrical potential. Okay, so they're all there and they're trying to get off, and they're looking for somewhere to go. Now we've got the air here. Electricity doesn't pass through the air very well, but it can pass through the air if we've got a high enough electrical potential. So now I've got another piece of metal here with a wire on the end, and the wire plugs into the front of the Van der Graaf, and that is at 0 volts. In other words, this thing here has got no charge. It's got the same number of protons as electrons all the way up and down this piece of metal. So if I was to turn this thing on, it might be a little bit noisy. There's a switch there. Now this thing here is building up a big charge. So there's lots of electrons going around the outside here, and they want to get off. And if I move close here, I don't know if you can see that, possibly hear that, but some of the electrons are jumping off. Let's see if I can do it with this thing here. There. So very high electrical potential. This has got no electrical potential because it's at 0 volts. It's got no spare electrons or anything like that, and so there is a big difference in the potential of this bit here, which gave me electric shock, and this thing here. Very high potential, very low potential, so there is a large potential difference. So large that the current doesn't even need a wire. It can just jump across the air like that, and it jumps. If I was to touch it on here, then the electricity, the electrons that are building up around here, just because this is touching, it's running straight down there, straight down to the 0 volts, which is down here, and that is an electric current flowing around there. It flows from an area of high potential to an area of low potential. So I'm holding onto this. Let's see if I can. So because I'm holding onto this, it's jumping from me across my chest and down and through here, but you get much bigger whack if you do that thing. Yeah. So let's turn that off. A little bit electric shock. So there you go. We tend to think that static electricity and what we call current electricity, electricity that makes bulbs come on and motors go around, are two separate things, but they're not. What this thing is, it's static because such a big charge builds up and then it tries to find somewhere to go. But if you don't have such a large charge, such a high voltage, which this would be thousands of volts, not a lot of energy in there, but thousands of volts. If you have a smaller voltage, like 1.5 volts that you'd have in a little battery, a little AA battery, then there's no way that you can get a spark jumping off from one end of the battery to another. But if you connect it to something like a piece of wire, which is a good electrical conductor, then what you have is the difference in the potential from one end of the battery to the other tries to even out. Electricity tries to flow from an area where there's high potential round to an area where there's low potential. And that's what we're saying when we're talking about potential differences, the difference in potential between 2 points. So this Van der Graaf could be at 5,000 volts. And if I had something else which was at 3,000 volts, there's still a difference in potential between the two. And if I put a wire between it, the electric current would flow from high potential to low potential because there is a potential difference. So we've got voltage, that's how big the potential is. And the potential difference is measured in voltage, the difference between the two. Charge is actually how many electrons we have managed to build up around here. If you are charging your phone, I want you to think about the battery in there just being topped up, one end of the battery being topped up with loads and loads and loads of electrons. And so that end of the battery has got more electrons than the other end of the battery. And if you connect one end to the other end through your phone circuits and things, then all those electrons which are at one end will flow through to the other end. And while they're flowing through, they will be doing things in your phone. So potential difference makes a current flow. Not everything conducts electricity as well as a piece of wire. I told you about this thing here, doesn't conduct electricity at all. It's got a very, very, very high electrical resistance, whereas a piece of copper wire would have a resistance of virtually nothing because electricity can just whiz straight through it without any problems at all. You and I have got a reasonably high electrical resistance. You need quite a high voltage, at least about 50 volts, before it does you any damage, but you can pass electricity through you, which is why we can get electric shocks and get electrocuted. So we've got a reasonably high resistance, but not as high as this thing here, so we can still get affected by it. The other thing is power. If you had, say, a 10 watt light bulb, that means is how quickly it uses the electrical energy. We don't say it uses it up, but it uses it. It turns it from electrical energy into light energy. And if it's 10 watts, it's using 10 joules of energy every second, turning that into electrical energy, into light energy. And some things use more power than others. An electric kettle, for example, has got a big fat lead on that, and that's because you have to get a lot of electricity down there in one go. It uses an awful lot of energy every second. It will use about 2,000 joules of energy every second, so a 2 kilowatt kettle, that's what that is. Right, so now when someone talks to you about electricity and potential difference, I want you to think about this thing. There's a high potential, and the little one thing here had a low potential, and if there's a potential difference there, an electric current will try and flow from one to the other. Got it? I'll do some more of these soon. Take care.